Reviewing the Year 10 end of Term 3 test, starting with the structured questions. Question 1 asks you to describe how the student could measure the volume of the piece of rock. Now, the first clue here is you're being asked to measure, not calculate, measure. The second clue that this isn't a straightforward, simple answer or a quick answer is that it's 4 marks. So you're being asked to describe a method here to measure the volume of a piece of rock. Why a piece of rock? Because it's an irregular shaped object. So key points in this: you will fill a Eureka can until it stops dripping. You will carefully lower your rock on thin thread. You will capture the water that spills out in a measuring cylinder. And the volume of the water equals the volume of the submerged rock. Now, this is a classic 4-mark or 6-mark question. So it's not about making 4 points so much as giving a working method with enough detail. So this is all you need. This could have been a measuring cylinder. You could have said that you'll take your measuring cylinder and you'll put the water in there, and you get your eye level with the meniscus, bottom of the meniscus, and read off your first volume. You stick the rock in, and you get your eye level with the meniscus, and you read off your second volume, and the volume of the rock is the second volume less the first. So that's also a perfectly valid method. You don't have to use the Eureka can at all. You can just have a measuring cylinder into which the rock will fit and do this. Now, it's not clear from this question what level of detail you need. The idea of the eye being level with the bottom of the meniscus, the idea of the Eureka can stopping dripping. I would also, if I was you, be talking about the can being on a level surface. Carefully lowering the rock in on a thin thread, carefully lowering so you don't spill any thin thread, so the volume of the thread does not significantly affect the value of the volume that you measure. Capturing the water that spills out of the measuring cylinder, or into the measuring cylinder, and then saying that the volume of the water is the volume of the submerged rock, or the volume of the rock. It's a difference between the two volumes. So that's what you're after. This is a method that you are required to know. So you just need to remember it, learn it. Part B, the volume of the piece of rock was 18 centimeters cubed. The mass of the rock, 48.6 grams. Density is mass over volume, and that gives you 2.70. Now, you should always be ready to write the units down. This is in grams, this is in centimeters cubed. I've divided this by this, so my units are grams per centimeter cubed. Might have been kilograms per meter cubed. Make sure that you're always thinking about the units. Part C. Densities of different rocks. Which is most likely the type of rock the student had? Well, we need a density that is similar to 2.7. And what have we got? Well, limestone is very close to 2.7. The others are all further away. So we'd say limestone. One source of error. Now again, note it says source, not type. So whilst a lot of the time we're looking for systematic or random or zero, never human, that's a type of error, not a source of error. So what's the source of error here? Well, if you talked about getting your eye level with the meniscus up here, if they didn't do that, that would be a source of error. The position of the eye around the meniscus. If your Eureka can was not absolutely full to overflowing, if you didn't overfill it and then wait until the spout stopped dripping, then that would be a source of error. If you didn't collect all the water, or of course if the can was, if the measuring cylinder was already wet, that would be a problem. So we're looking for sources, not types, right? How would the error you described in D affect the measured volume of the rock? Well, it would be too big or too small, depending, of course. The eye position could do either. The level of the water in the Eureka can, well, if that level was too low, then the volume that you would get would be too small. If you didn't collect all the water that was displaced, it would be too small. If the measuring cylinder was wet before you started, it would be too big. So the answer to that question, part E, really depends on what you said here. And you should try to be specific. Answers like changes, it would change the volume. No good. It's almost never acceptable. I can't think of a circumstance where changes would be acceptable. This links back to this. So the eye position could make it too big or too small. The level of water in the Eureka can, well, that can only ever be too low if it's not right. Therefore, the volume that you would measure would be too small. If you didn't collect all the water that was displaced, if you forgot to put the measuring cylinder in before you put the rock in and then quickly put the cylinder in later on, some of your water will have been lost. You won't collect it all. Or, and that would make your volume too small, of course. Or, of course, if the measuring cylinder already had water in it, then the volume that you would measure would be too big. And that, of course, would be a zero error. Question 2. A 12-volt filament bulb connected to a 12-volt power supply. The graph shows how the current changes after the bulb is switched on. After 0.1 seconds, the bulb works at its normal brightness. What is the current through the bulb when it is working at its normal brightness? So we come up from 0.1 and it is 1.7. So that's just straight reading it off the graph, but taking careful note of the scale. 5 small squares to 0.02, so 2.5 small squares to 0.01. The bulb works at normal brightness for 30 seconds before being switched off. Calculate the charge that flows through the bulb in the 30 seconds. Well, Q equals IT is what we're after here. So the current 1.7 times 30 seconds, 30 times 0.7 gives you 51. 1.7, sorry, gives you 51. And the units are capital C for coulombs or all lowercase coulombs. And I would look to make that more obviously lowercase. Calculate the energy transferred by the 12-volt bulb when it's working at its normal brightness for 30 seconds. Well, your energy would be the charge times the potential difference. 51 coulombs pass in that 30 seconds, and 12 joules per coulomb of work was done. So 51 times 12 will give you 612. Now you need to know your equations because you're lost without them here. If you just look at that, 1 mark you could have had out of that if you didn't know your equations, but you knew your units. Part B. Between 0.02 seconds and 0.08 seconds, there is an increase in both the resistance and the temperature. Explain, in terms of the electrons and ions inside the filament, why both the temperature and the resistance increase. Well, I would say the electrons collide with the ions, and notice we have to talk about ions, not atoms. It says so here, but even if it didn't say so, using the word atom here would get you no credit. So the electrons collide with the ions, they pass on kinetic energy to them. The ions vibrate faster, and again note they were vibrating and now they're vibrating faster. To say they start to vibrate is wrong because they were vibrating before. And temperature is a measure of the average kinetic energy of the ions. And since the ions vibrate faster, more, bigger amplitude, the electrons collide with them more. Which leads to an increase in resistance. Now, electrons collide with the ions, passing on kinetic energy. 1 mark. Ions vibrate faster. 1 mark. Temperature is a measure of the average kinetic energy of the ions. 1 mark. Since the ions vibrate faster, the electrons collide with them more, which gives you an increase in resistance. So there are 4 possible marking points here. You need 2 of them. You need 1 of them on resistance because you're asked to explain both, and 1 of them on the rise in temperature. So you're going to have this bit plus 1 of these 3. Question 3. Why could this system of using the black surface to heat up in the sunshine and store that energy in the soil under the road surface, and then use that stored energy to melt ice. We need to be careful how we answer this. We're looking at thermal energy. We're looking at infrared. That's where we're pitching at. So black is a good absorber of thermal or infrared radiation. Now, an example of something that is not acceptable is light. Light does not make things warmer. It is infrared, otherwise known as thermal. Infrared is better. So be careful how you express yourself here. It's not about the light, it's about the infrared that comes with the light. What is meant by the specific latent heat of fusion? Well, it is specific latent heat and fusion. So it is the energy required to convert 1 kilogram, there's your specific, of solid at its melting point to liquid without change in temperature. Now, you might get away without that bit. You can usually get away without that bit, but you should know this definition. The specific latent heat of fusion of a substance is the energy required to convert 1 kilogram of the solid at its melting point to liquid without change in temperature. So there's a mark for that, and there's a mark for the solid to liquid. Okay? But you might not get away without that. And if I wrote the question, you wouldn't. Calculate the amount of energy required to melt 15 kilograms of ice at 0 degrees C. Well, the energy is, of course, the mass times the specific latent heat of fusion, which is 15 kilograms. It is at its melting point, times 3.4 times 10 to the 5. And that gives us 5.1 times 10 to the 6 joules. And of course, we're given the units, but always think about your units. Another way to keep roads clear of ice is to spread salt on them. One variable that the student should have controlled. Well, the amount of ice, the mass, volume, quantity of ice. Ice is the key word here. You might have said weight as well. During the investigation, the students stirred the crushed ice. 2 reasons why. Well, to distribute the salt through the ice and to keep it all at the same temperature. Describe the pattern as the mass of salt rises, the melting point falls. That's all you can say. You cannot say proportional, because it clearly isn't, or inversely proportional, because again it isn't. It is not falling by equal proportions. So it is not inversely proportional. So don't try to be clever unless you know it's inversely proportional. Don't say so. Undersoil electric heating systems are used in greenhouses. The system could also be used under a road. A cable just below the ground carries a current. There's a power of 500 watts. I'm going to convert that straight away from kilowatts to 500 watts. And the time is 2 minutes, which is 120 seconds. We have to do it in seconds because this is joules per second. So the energy transferred would be power times time is the energy. So 500 joules per second by 120 seconds gives us 60,000 joules. Note, you're asked for it in joules. You might get away with 60 kilojoules by putting a K in front there, but better to give the answer in the terms you're asked for it. Moving on then to the multiple choice questions. Question 1. A wooden block has a mass of 2 kilograms and a specific heat capacity of 2000 joules per kilogram degree C. Calculate the energy needed to raise its temperature by 6 degrees centigrade. So we have energy equals mass times specific heat capacity times change in temperature, which is 2 kilograms times 2000 joules per kilogram degree C times 6 degrees. So that's 12 times 2000, 24,000. The answer is D. Question 2. Which letter A, B, C or D shows the part of a circuit that carries a current of 2 amps? Well, you've got 5 amps here, 2 amps here, 3 amps because 3 and 2 make 5. So you've got 3 amps here, 5 amps here, it's D. 2 amps flows into the resistor, 2 amps flows out of the resistor. That's always the case. Question 3. A student has 3 identical resistors, 4 different arrangements, which give us the highest resistance. Well, parallel will give you the lowest resistance. So 3 in series would be the highest. Here we've got 2 in parallel and 1 in series. 2 in series in parallel with 1. So all of these are going to have smaller resistances than B. So question 3, the answer is B. Question 4, here we have a temperature time graph. We have that characteristic flat period of time, no temperature change. So here we have a change of state. The temperature is falling, so here we must be freezing. So 4, the answer is B. Question 5, we have 44,000 coulombs flowing through a light bulb. We have 230 volts. Calculate the energy. And 2 sig figs. Well, energy would be charge times potential difference, and if you do that you get 10,000 kilojoules or 10 million. So the answer is C. Question 6. What are the units of specific heat capacity? Well, joules per kilogram degree C, you need to know that, so the answer is A. Which equation links charge, flow, current and time? You should know that. Q equals IT. QIT. Question 7, the answer is C. Question 8. The power of a washing machine varies between 0.7 kilowatts and 2 kilowatts depending on what part of the wash cycle is operating. Maximum current would be when the maximum power is being delivered. So here you have to know that V is 230 volts. That is a fact that you need to know as part of the specification. You need to know that power is V times I. So the current then is the power divided by 230. So if you divide 2 kilowatts by 230, then the answer you will get is 8.7 amps. So the answer is B. Question 9. Domestic wind turbine has an electrical resistance of 23 ohms. Generates a current of 11 amps. So we have a resistance of 23 ohms. We have a current of 11 amps. And we want the power. So you could say power is I squared times R, or you could say power is V times I, but V from V equals IR equals I times R, which then gives you I squared R. Either way, 11 squared times 23 is the power, and that is 250. Kilowatts. That's 121 times 23, 250 kilowatts. Question 10, the LDR, of course, is D. You just need to know that. Question 11 then. We have 12 volts across both bulbs. They are in parallel. So there's 12 volts across C and 12 volts across D. We have 5 amps flowing in here, 3 amps through C, which leaves us 2 amps flowing through D. We want the resistance of D. We're going to say that V equals IR, which gives us R equal to V over I. V is 12, I is 2, R then is 6 ohms, and the answer is C. Question 12. We have an energy of 18,400 joules. That's being supplied to, well, the difference between these two masses is being evaporated. So we have a mass equal to 0.152 minus 0.144, and 0.152 minus 0.144 is 0.008. And we want to know L. We know that E equals ML, we're told that here. So we've got 18,400 equals 0.008 times L. So L then is 18,400 divided by 0.008. And if you do that, you'll get 2.3 times 10 to the 6, 2.3 million. Question 13. Wood has a density of 180 kilograms per meter cubed. So the density is 180 kilograms per meter cubed. We want to know the mass. We know that density is mass divided by volume, and the volume is the length, and we want this in meters, so 0.2 times the width, 0.3, times the height, 1.2 meters. And if you multiply all that together, the mass, of course, is density times volume. So multiply all of that by that, and you will get B, 12.96 kilograms, which is about right for a lump of wood like that. Question 14 then. We have a current of 0.15 amps, a PD of 2 volts. We want to know R. We're going to say V equals IR. So R is V divided by I, which is 2 divided by 0.15, and 2 divided by 0.15 gives us 13.3. Finally then, question 15, we have a current of 40 milliamps, that's 40 over 1,000 amps, and we have a charge of 3.6 coulombs, and we want to know how long it takes for the 3.6 coulombs to flow at that. We know Q equals IT, so we know T is Q divided by I, which is 3.6 divided by this, which is times 1,000 divided by 40. Or work that out and divide 3.6 by it. So 3,600 divided by 40 gives us 90. And it's seconds. So the answer is